high up in the sample you go, the sample gets more and more displacement. So the displacement, if I took any particular cube of sample and said, what's the strain on this? It's the displacement divided by the height of the sample. So that would be deformation over the gap in this case. And so that's unitless. You've got basically maybe 0.5 millimeters over a 1 millimeter gap, let's say, and it would give you 0.5 strains. Now, the other thing that we would need to quantify is the stress. That's the amount of force applied per unit of area. So if you had a larger plate and you were applying a force on it, a certain force on it, it would be dissipated across the big space, a big area, and so you'd have a lower stress. But if you have a very small plate and apply the same force, then you'd have a high stress. So the force in pascals divided by the area in square meters gives you, sorry, newtons divided by square meters gives you the unit of pascals. And if you displace to something like a gel, obviously it's going to move and stop if you just apply a small force to it. But if it's a liquid and you apply a force to it, it keeps on flowing. And so we could describe that in terms of the number of strains per second. And this is my first mistake here. This is a shear strain, not a shear rate, actually. So the strain is deformation over the height, and shear rate would be the number of strains per second, or deformation over the gap times the time taken there. So if it keeps on flowing, then we have a shear rate, and you could define a number of strains per second. And so it has the dimensionless unit of strain divided by seconds of time, so you have reciprocal seconds. Now, it's actually fairly easy to calculate the shear rate of most processes. And so one thing you may have done this morning is spread some butter on your bread. And so we could do a calculation here just to show you how easy it is. Now, let's say I move my knife across that bread surface at 3 centimeters a second. So that's 30 millimeters. We put everything in millimeters. And maybe that film of butter is on average 0.25 millimeters thick. So we basically divide the lateral speed divided by the gap, basically just like on the sideways speed divided by the gap. And that gives you this shear rate. So it's 30 millimeters per second divided by 0.25 gives you 120 reciprocal seconds. So you can think of that as an easy way to calculate things. And you could calculate flowing through a tube as well. This is a similar calculation, just slightly more complicated, called Poissonian flow, or Poisson's flow law here. So we see the volumetric flow rate is Q. That's how many liters or whatever per second you're giving it. The radius of the pipe cubed, that's r cubed. And then that's the shear rate equals 4Q over pi r cubed. That's for a Newtonian liquid. And if the material is non-Newtonian, maybe it won't give you quite the same parabolic flow profile. Maybe it will be slightly flatter on the top. And so you can correct for that. If you know the n value, that's the shear thinning factor, you could do the flow curve first, calculate the gradient from the flow curve, and then do a corrected shear rate. That's this is the apparent shear rate, gamma dot A, and the corrected shear rate is gamma dot C. And so the formula for n is d log tau over d log gamma dot. So those are how you calculate shear rates in some processes. If you look in textbooks, you'll find shear rate calculations for almost every type of configuration, maybe, through a slot or through a U-tube and coming out of, nozzles and all sorts of things. So it's actually quite easy to calculate shear rates in different processes. And if you need help doing that, please let us know. Now, if you look at most samples, they have either a Newtonian viscosity, where it's independent of shear rate, or they're shear thinning. And if your sample is Newtonian, actually you don't really need a high cost rheometer. You could just use a viscometer, right? Because the shear rate at moderate shears is the same as the viscosity at high shears and low shears, whereas a rotational rheometer can measure over a wide shear rate range. So with this instrument, we can calculate the viscosity while it's almost stationary, and also up to very, very high shear rates, simulating pumping, mixing, or brushing. and spraying and things like that. So if a viscometer maybe goes from 0.1 to 100 reciprocal seconds, a rotational rheometer goes from about 10 to the minus 6 up to 10 to the 5. So you can get about 11 orders of magnitude from this instrument. And you can actually simulate these processes. It's very useful. Now, if you really want to get to ultra high shears, then the capillary rheometer comes into its own here. And that's where you're squeezing a sample through a small die, almost like out of a syringe. But it's an instrumented instrument, obviously with transducers and pressure and controlled speed and temperature. And so we can generate up to over 10 million reciprocal seconds with capillary rheometer. Now this is a viscosity flow curve for half and half, something that we use very commonly here in the USA in our coffee. It's half cream and half milk. And this flow curve is generated between 10 reciprocal seconds and 10,000 reciprocal seconds. So this would be pouring, this might be mixing, pumping, this would be a high-speed mixing, this would be blending it, you see, as you can see whether it's lower viscosity or higher. And you see it's fairly Newtonian, but there is a little bit of structure at the low end, maybe going up to 3 centipoise of viscosity and coming down to about 2.2 centipoise at the moderate to high shear rates. So you see, with something quite dilute or not a lot of gel structure in it, it's going to be fairly Newtonian. And if there was any particles in this, obviously they would sediment. You'd see them probably sediment to the bottom. If you wanted to thicken it up, then you'd obviously need to add some thickening agent to make this higher viscosity on the left-hand side. So we can look at things like storage stability and sedimentation that happens over months on the rheometer, and you don't have to do months worth of testing. You can actually run a very quick test, maybe 10 minutes or half an hour, and determine which samples are going to be stable and which ones aren't. And I'll describe this. So sedimentation usually occurs if the particles are bigger than a micron, unless they're density matched with the suspended medium, or if there's some body in the sample to prevent it from sedimenting. So if it's a weak gel, maybe the particles don't sediment, and if they're density matched, they won't. But that's unusual that you can actually density match your particles in the medium. But sedimentation is probably one of the most common issues that we hear about with storage issues. If the particles are less than a micron, by the way, you will never get sedimentation unless they start to agglomerate or aggregate together. And so that would be a zeta potential phenomenon. You need to charge them up so they repel one another, and then they won't sediment. But if they're bigger than a micron, they will. And so one thing we should do is let the sample get to thermal equilibrium when you first loaded it into the instrument. And then you want to resuspend it, right? Because your sample particles will be at the bottom. You won't get a very uniform representative sample there. So you might want to shear it with a spirally grooved bob. This will actually resuspend the sample after it's at thermal equilibrium. And then you can go into your viscometry testing as normal. Maybe give it a minute to rebuild after doing that resuspend, and then you can make a test. So as I was saying, if you want to keep samples from aggregating, if they are submicron, you could do that by charging them up, increase the zeta potential, or so that it's either very strongly positive or strongly negative, so that they repel one another. You could sterically stabilize this product by attaching things to the surface so they just can't aggregate. Or you want to increase the viscosity of the continuous phase, or by putting a weak gel structure in there to prevent the sample particles from sedimenting through it. So all of these things are commonly done in your beverages and around us. I'll have a slide in a minute to show that. But what we're saying here is we want to introduce a very weak yield stress. So this material won't really flow. This is shear rate. So it's not really doing any shear rate until you reach the yield point, and then suddenly it starts to flow. Now we're all familiar with this. For instance, with butter, right? You push on it a little bit, it doesn't flow. Push on it harder, it doesn't flow. When you push hard enough, it starts to spread out, right? So that's the yield point, the force required to start it flowing. And but you actually can get that in beverages, but it's such a small yield stress, you can't really see it it's just enough to keep the particles suspended. And so one of these vanishing yield stresses, as we call it, gives it maybe a nice mouthfeel, might feel a bit thicker and creamier. It also determines how hard it is to pump something or how easy it is to stir something. And it also tells you whether it's likely to be settling or not. So in a quick force balance equation, we have a couple of forces here. We have the gravitational settling force, we call that Fg, and then we have the buoyancy of the medium on that particle trying to suspend it. We call that the normal force, Fn. And if Fg is greater than Fn, then this particle will sediment, right? And if Fn is greater than Fg, then it should stay put, or it will even float up. So what we have here is for a static dilute hard sphere suspension, this is obviously very simplified, we can see the density of the particle, rho d, and the density of the continuous phase, rho c, and times the radius of the particle times gravity, 9.81, divided by 3, we get the sedimentation stress. So if you like, that's the stress of the particle pulling downwards. Now, if the yield stress of the medium is higher than the sedimentation stress, then that particle should never sediment. It should just stay put. So it'd be like peas, for instance, trying to sediment through hair gel. They shouldn't be able to move because the gel's just too stiff. But if you put peas in a low viscosity liquid, a thinner soup, for instance, then the peas will sediment to the bottom. So this is a pretty quick calculation to do. You just need to know the particle size and the density of the P and the density of the continuous phase, and you can do that calculation. This is just showing you one of the Procter & Gamble patents here for thickening up beverages. Very interesting that they do this. And so you see here they've got 3 thickeners. There's the propylene glycol alginate, which is a surface active thickener, xanthan gum, which is a pseudoplastic or shear thinning thickener, and guar gum, which is a Newtonian characterization thickener. And by mixing these together in certain quantities, you can actually stabilize this beverage. So the surface active thickener will make it a stable oil and water emulsion, and then the other thickeners give it a nice mouthfeel and without excessive amounts of thickness. So you can still drink this, but you'll see this sort of thing going on in things like Sunny D or Tropicana, even, you know, Tropicana juice that you might think is just pure orange juice. If it didn't have any thickener in it, you'd have all of the pulp at the bottom and you'd have a fairly clear liquid above that. But by thickening up, it kind of becomes a richer, thicker looking drink. Now, so that was looking at sedimentation stability with a rheometer, and that's one of the things you can do. As I can answer questions about that later if you like. Now, another thing that people do is look at the surface tension with a Dunois ring. Now, surface tensiometry is when you lift something up through the surface, you can see how much liquid it will lift up. So let's say this was half full of water, and you're pulling your Dunois ring, which is a platinum iridium ring, out through the liquid. It will actually lift up a meniscus a little bit, and then obviously as it goes up higher, it will break. And you'll see the normal force start to go negative. So here, as we lift up the ring, this is the gap opening up with time and seconds. So that's the blue line is gap. And then the force in grams shows a little bit of a noisy trace here because we're looking at very close up on this graph. And we can see it's not really doing anything. And then as it lifts out of the liquid, it starts to lift a meniscus. And then it gets high enough and then it snaps. So now the Dunois is outside of the liquid. This is as it's coming up, it's lifting a meniscus. So we fit a second order polynomial here, and we find the minima of this second order polynomial, and we find the average of the first 15 seconds of that graph. And from the difference between the normal force at the beginning and during lifting the meniscus, you can see how much of the liquid was lifted up by surface tension. And then you use a calculation as calculated by Dunois, and that will show you what the surface tension is. Now, it's actually quite useful because if you have a low surface tension, you can wet surfaces out. So, for instance, fruit is often sprayed with a polysaccharide spray, and you want that to give a nice uniform coating across the whole surface. You don't want it to have just spots of polysaccharide and then gaps where the sample will, well, the fruit here will oxidize in spots, but not in other spots. You want it to be uniformly coated, and then it will last much longer on the shelf, and you don't need to apply so much of it. So this is taken from Wikipedia. This is a list of common surface tensions. And so what we would use is the Denoy ring, and we'd maybe run water initially and see, am I getting about 75 or 76 dynes per centimeter? That's the common unit for surface tension. Or maybe I would use glycerol or one of the other liquids, if you like. Obviously, water is pretty good because it's got a very high surface tension. You could use mercury, but it's a bit hazardous. So obviously this is temperature dependent. As you heat up water, surface tension goes down. So you do need to set the temperature isothermally during one of these tests. So you can do this with the Denoy on the connexus. This is the setup. And there's a sequence that does this for you. Very useful. Now, when you do a viscosity flow curve, one of the first things you need to do is stop the sample from slipping. So if you imagine this kind of cream here, this would be a creamy liquid, and you can tell it's got a low viscosity slip layer on it there. If I tip that spoon up, this thing would probably slide off and leave a fairly clean spoon. Unlike yogurt, which might just pour off in drops. This is going to slip off. And if this happens when you start to spoon your product around, you can tell, oh, okay, it's probably going to slip on my plate. So instead of giving you a laminar flow field between the plates, we'll get slip on the lower plate and slip on the upper plate. And so that won't give you the right result. That will give you just the viscosity of the slip layer and very little viscosity of the actual thicker cream material, the bulk viscosity. And so we need to stop it slipping. And we do that by using serrated or roughened surfaces. And obviously the sample trapped inside the serrations doesn't move. It gets stuck in there. And so we use the effective gap as from the tip to the bottom tip here. That's the gap of the sample that's actually flowing. So lots of materials slip. Either they melt like ice when you're ice skating, just the surface of the ice melts, or maybe it goes through a phase separation. And in this case, you've got some liquid coming out of the bulk material. And so that causes a slip plane between the measuring systems. And so by accommodating that liquid in this surface roughness, we actually grab hold of the bulk of the sample and then eliminate it. So this is how the results would look. If you ever see a viscosity flow curve like this red one with a double knee, so you've got a viscosity drop, a plateau, and a second viscosity drop here, this is a big red flag. This would show me, hey, this could be slipping. It's possible, of course, that this could be macrostructure breaking down and then microstructure, but actually probably likely to be slipping. So what we'll do is we'll use a serrated or roughened measuring system. And if you get the same viscosity flow curve again, then it really was a material phenomenon. It wasn't a slip. But if you get a different shape curve, then you know it was slipping. And actually now we've resolved that slip issue. So what you would do is actually go to rougher and rougher measuring systems until the shape of the curve becomes the same. And then you know you've resolved the slip issue. So this is viscosity is eta in Pascal seconds against shear stress. Okay, so this is some work we did on yogurts, popular brand yogurts. And we're just measuring with a plate 40 serrated upper and lower measuring systems from 0.1 to 1,000 reciprocal seconds. And it was 20-second delay per point and 10 seconds integration time. We did it at 20 degrees C. And you can see here that the materials are all very shear thinning and actually pretty similarly shear thinning. And these are different products. We've got Danone, Yoplait, and then HEB, which is a company in Texas that make fruit on the bottom and other things like this. So the Danone yogurt, you see, is very shear thinning. but not maybe as quite as shear thinning as the Yoplait, which is in black here. And the HEB is very similar. That's the key lime pie in green, and the fruit on the bottom strawberry in red, very aptly colored. So we can see here from the low shear viscosities how it might sediment or settle. I mean, maybe you should have gone lower and lower to get to the really, but it's going to give you a good indication at 0.1 of the order of these sedimentation stability. And obviously the fruit on the bottom is thickest, so it's least likely to settle. And the pumping and mixability is going to be shown from maybe 500 reciprocal seconds here. And then the mouthfeel, according to Professor Jim Steffi, is about 60 reciprocal seconds. So that would be if you want to swallow a drink or whatever, you can get the mouthfeel from that shear rate. And so we can see from the order of these how they would mix or what their mouthfeel will be like. And whether it's nice mouthfeel or poor mouthfeel is really subjective. And maybe you want to use a taste panel initially to get an idea of what's a good mouthfeel and what's poor mouthfeel. So if I take those bottom points of the flow curve there and measure off their viscosities, they all look pretty similar because it's a log scale. But when you actually look at the values, that's 250, 400, 440, and then 800 Pascal seconds. And I understand that the fruit on the bottom, the red curve, they actually wanted it to be extra thick because they didn't want the fruit to get mixed in. They wanted it to be a layered yogurt product, whereas the other ones were fairly uniform. It didn't really matter if they mixed up a little bit during transit. Now, another good use of yield stress is to look at enrobing. So for instance, this is a Mars bar in England, or here it's called Milky Way, and it's a nugget and then a caramel, and then it's enrobed with chocolate, and it gives you these ripples on the top. This is obviously very aesthetic, and if you have extra thick chocolate, you maybe think that you got a good one, you know. When they first developed the Milky Way bar, they found that it wasn't giving you the ripple size that you wanted, and it was actually running down and giving feet on the bottom. So in the old days, you'd get a little meniscus, if you like, of chocolate on the bottom. They called it feet, and they wasted, they said, millions of dollars worth of chocolate per year by doing that, where they were trying to get the stand-up properties on the top. So they changed the emulsification process and used a rheometer. At that time it was from Bolin, and they reformulated to give a higher yield stress. And so that shows you its stand-up properties. And another application would be for frosting a cake, for instance. You want it to have a nice stand-up property so it looks thick and creamy. And but obviously those things are a little bit temperature dependent, right? You could frost a cake and take it out on a hot summer's day for somebody's wedding, and then maybe it will all melt, right? And it will flow down here and you have a puddle of frosting. So these things are important to characterize. And so this is the yield stress. We're doing a stress ramp here with viscosity on the left-hand side. And I did it in duplicate. You see the red is one set of tests and the black is another. Got fairly good reproducibility. But at 20 degrees C, you see a fairly high yield stress. At 25, it's dropped off quite a lot, 30, 35. And by taking the viscosity at a certain shear rate, I think I took it about 5,000 here, and I could plot them all with yield stress versus temperature, and then you could see how temperature sensitive this frosting is. And so that would give you, the more temperature sensitive it is, maybe it will give you the melt in the mouth properties, you know, that it gives you good mouthfeel. But it also could be a little bit difficult to manage if it melts at too low a temperature, like the wedding cake on a hot day, something like that. So by adding different things into the formulation, you can change the temperature dependence of that frosting. This slide looks like it got out of order, but I think this is also yield stress. So as I'm increasing the stress on the sample, you can see it starts to flow, and that's the yield point there. And this black one maybe around 12 or 10, and then the Yoplait maybe around 15 or 17. and then key lime pi maybe just over 20, and then the HEB maybe 35. So this really does have a high yield stress in the blue one there. So another thing that you might want to look at, not just the yield stress, obviously that was important, but it's the rebuild, because we're squeezing this frosting out through a bag and it's going through a nozzle and it's getting some shear, and it breaks down to a degree as it comes out through a small nozzle, and we want it to rebuild immediately, so it gives you the sharp edges that you prefer on these cupcakes in this case. Now you can do a simulation of this on a rheometer by applying a single shear rate and then stopping. So that would be like piping it, right? That's the shear rate, is piping it. And then you go into oscillation. And the oscillation basically just does a microscopic oscillation on the sample, almost like being stationary, but you can watch rebuild in real time. So what we'll see here is a good frosting obviously will rebuild very quickly and it shouldn't sag or slump, but a bad frosting might rebuild more slowly, and so it could sag down or whatever a little bit. So the rebuild time is important. So that's what we're looking at here. And you can also look at the modulus before shearing. So this is the elastic in red here, and you see this is 30, 40, so this is about 35 kilopascals of G prime shear modulus. And then after shearing, you see it broke down to around 15, and it's rebuilding fairly quickly, back up to about 30 after 3 minutes, and then rebuilding more and more. Eventually, obviously, it will get back to its original structure. And then by, you can see then how much it broke down by piping, how quickly it rebuilds. But the fact that it's elastically dominated right from the beginning, the G prime value exceeds the G double prime value, that shows it's unlikely to slump too much. So if you start off with a viscous product and then the elastic modulus overtakes, let's say the elastic modulus was down here, then actually that would be slumping for, you know, so many seconds, and then eventually it will stop slumping. That's not what you want to see. So this is quite a good product. You see it does break down a bit, but it rebuilds fairly quickly, and it's going to get back to its full structure in 10 minutes or so. Now, another thing that people often add is gums, and we do jellies, we do cake toppings, and all kinds of different things with gums. And so the gelation time is a very good thing to be able to characterize. Now, one thing that has gummy type property in it, actually, you maybe don't think of this, but it's starch. So if we have a starch paddle here, this is a direct replica of the RVA, the rapid viscoanalyzer. And you put this cup together, it's got a removable base here, in 3 pieces. And then you put the liquid in, water, and then you put in the starch potato powder, and then you spin this around, and it actually mixes everything up. And then the temperature ramps up heating, and then we'll see the gelation. So this is a standard method which was developed by A.E. Staley, and they were the people that first developed this rapid viscoanalyzer. And the idea is that you heat this up from 50 degrees to about 95 degrees. This is simulating cooking, kind of like in gravy, you know. You thicken it, you heat it up, and certainly a certain temperature, maybe 75 degrees or 80 degrees, you see the amylose structure start to break up, and you see that it really thickens up here, the starch thickens up, and then it actually starts to drop off again. So it goes through this maxima, and that is actually one of the QC criteria. What was the viscosity at the maxima? You hold it, and then it goes down through a minima, and that's another viscosity point, and then you cool it down again to 60 degrees C and hold it, and then it gets to a final viscosity. So from the maximum and the minimum and final viscosity, you can characterize the starch's properties. So this is just a quick test for a rheometer, but that might save you having to buy a completely separate instrument to do starch testing if you wanted. Now, another way that people do gelation, obviously, is to do this oscillation. As I said, if you're shearing a sample round around, you're going to break down some of the microstructure. And maybe you don't want to do that. Maybe you want to look at the gelation as it occurs without breaking the sample. And so we do oscillation. So these are microscopic oscillations. And as the sample oscillates, you can watch the structure real time. So here we are, oscillating the upper plate to the right and to the left, rotationally. And it is really a microscopic movement. You'd barely see anything going on. And we are applying a stress wave, and we're measuring the strain that resulted, right? If the sample is soft, obviously it moves a lot. And if it's very stiff, it doesn't move very much. So the ratio of the stress amplitude to the strain amplitude gives you the modulus. And we can actually obviously control the strain and see what stress was required as well. So this being a digital instrument can do either stress control or strain control. So you get the modulus, which is the stress amplitude over the strain amplitude. And you can control either. So the first test that people do here in an oscillation is they say, well, how much can I move my sample before breaking the structure down, right? If I do a huge oscillation, maybe it's breaking, so that could be too big. So the first test is, well, let me try really small oscillations and getting bigger and bigger and see what happens to the modulus. So as long as I'm not breaking it, then I'm working in what's called the linear viscoelastic region. So we do this amplitude with sequentially larger and larger oscillations. And initially you might get a little noise because it's not really moving. And then we'll get nice results, and it should be on a linear viscoelastic plateau. And then when you obviously get to big enough strains, the sample starts to break down. This is a bit exaggerated, but it would tend to start to taper off on the right-hand side. And so what we do is we say, okay, I can't really go past this strain without breaking the structure. So let's stick it someplace here on the linear region, and we'll choose a strain maybe here, and we can do all of our oscillation tests at that strain and know that it won't break down the sample. And so here's some example results. So we've got here a control and sample 1, and we've got test sample 2. Now the length of this linear viscoelastic region actually shows you an indication of the stability as well. So if the sample has got a very long linear region, then it shows that it's actually got a more robust structure, whereas this sample 2 has got a very short linear region before it breaks down, and so it's got a weaker structure. And so we can see that the control and sample 1 are likely to be more stable. This is similar to a yield stress test, to be honest, but done in oscillation mode. So to do a gel point test, we're going to oscillate within the linear region, and we can put our sample in. Maybe we cool it down over time and see what happens, or maybe we'll just leave it isothermally while it's oscillating, and we can watch if it just gels up with time. So you mix your samples together, whatever you expect to gel is going to gel, but it's going to do that in the instrument. So what happens initially is we have a viscously dominated product, that's G prime, is the viscous modulus, and the elastic is lower, but then it builds up and it crosses over. So now it's become a gel, and it's thickening up as it cross-links more and more. And eventually it plateaus here. This is when it's fully cross-linked, and now it's elastically dominated, and there's some viscous component, but it's not very high. If it's very elastic, then the G double prime would be down here, you know, the blue, dark blue one. So you can see the viscosity before, during, and after gelation. You can see exactly what time it takes for gelation to start occurring. And so this idea of a crossover between G prime and G double prime is commonly used in industry as the gel point time, this time here, which is just under 1 minute in this case. But if you want to be scientifically exact, you could say the gel time is actually when tan delta becomes independent of frequency. So you actually run the test at 3 different frequencies. As you go through the test, you'd go 0.1, 1, and then 10 hertz, and then keep going through these 3, scanning through these 3 frequencies. And when the results all coincide, that shows you that it's gelled right there. So that would be around 40 seconds in this case. Now, the nice thing about this, the independent of frequency, is you don't have to wait for the crossover. You see, you only see a crossover if the material is viscously dominated at the beginning, but sometimes it actually starts off as an elastic liquid, like with epoxy resin, it's thickened up. And even though it does go through a gelation process, it might go from an elastic liquid to a more elastic liquid. Whereas in this case, we can still see the time it becomes independent of frequency. The common use food gel is carrageenan. It's gone a little bit out of favor these days because of its side effects. Apparently not so good for your gut and things like that. But the nice thing about carrageenan is that you can really thicken it up or thin it down depending on the amount of cations in there. So if you add more calcium or potassium, it becomes a lot thicker. And also that increases the gelation temperature. So you can completely characterize this by just adding different amounts of calcium or potassium. So in this case, we've got 1% cap of carrageenan or 0.5%. You can obviously see the modulus is dependent on the amount of carrageenan in there, but also on the amount of potassium ions in there. So it's actually a direct relationship, or in this case. And there's another one, 1% kappa or 1% iota carrageenan with potassium ions or calcium ions. And you can see as you add more and more ions, it gets thicker. So this is a nice kind of tailorable thickener. You can really optimize its formulation properties by just adding slightly different ionic components to your mixture and get it to do almost anything else. And as it says here, few other hydrocolloids offer this flexibility. So as you saw before, people use also guar gum and xanthan gum and things like that, which may be better for your intestines. But just showing you how you could characterize gelation on a rheometer. So as we cool this carrageenan solution down, you see it's a very low viscosity liquid initially. And then as it comes down to this temperature, maybe 62 degrees C, it starts to gel up. And we see it going through that gelation process until it reaches about 43 degrees C, and then it's completely gelled. And so you can see it goes from 0.1 pascals to about 10,000 pascals. So really quite a comprehensive gelation test. And this is actually done on one of our lower end rheometers. So we should be able to do it even better on a Connexus and a Connexus Ultra. Another thing you might want to do here is look at the effective temperature. So if you heat your sample up, it thins down. You cool it again, it gets thicker. Heat it, gets thinner. Cool it, gets thicker. Now, ideally, this would be completely irreversible. You heat it and cool it, and it would go back to the same viscosity, right? So we're talking maybe 800, 900 pascals. Heating and cooling, it's gone up to maybe 1200, maybe up to now 1500 or 2000. So this is not perfectly stable, this control, but it's not very unstable, right? We're seeing the temperature go up and down here. The viscosity is going up a bit, but this other formulation, it starts at maybe 300 pascals, and then as we heat it up, it's really dropped off the chart, if you like. Viscosity fell down. This may be a little artifact result here. As we cool it again, now it's back up to about 600 pascals. So it's gone from 200 to 600, and then after the third, ramping up to 900. So this new formulation is much less stable. You see how the peaks in the yellow here have gone up and up and up. And the viscosity at the minima, I apologize for this poor data here. This is an old curve, but this might be useful as well to know how does the material behave in warmer temperatures. Now again, freeze thaw. So this is at 25 degrees C, and we're going to freeze the sample. So we cool it down to 5 degrees, and then we're going to heat it up to 25 again. Obviously, it takes a little while to freeze, so we just hold it there for a few minutes. And then we'll heat it up and cool it down, hold it cold again. And you can see here the viscosity initially is about 500 pascals. And then when you froze it, right, it becomes really hard. And then you melt it. And this is what we're interested in. How soft does it get, or how thick does it get? So it's gone from 500 up to about 3,000 pascals, and now it's kind of done. So what happens here is when things freeze and then thaw, they often phase separate. So you'll get gel particles and you'll get liquid areas in that mixture. So if you've ever frozen salad dressing and you take it out like a ranch or something, take it out of the freezer, you take off the lid and you tip it up, what will happen is that the liquid will come out right away, and it will mainly just be water, and then you'll have a very thick product left because it phase separated. So phase separation is your enemy in this case, and by formulating well, you can get rid of that. So mouthfeel, Jim Steffi generically said you can look at the viscosity at about 60 reciprocal seconds, which is useful to know if it's a drink. But another thing you might want to do is just actually simulate mouthfeel. You can do this on the rheometer. So this is done by Julian McClement's group at UMass Amherst, and a lady here called Cheryl Chung. I think she's graduated now. Yep, so you squeeze down on this sample to simulate the tongue coming up onto the palate with the food in the middle, and then it did a period of shear, and then it lifted up again. So this is a very good simulation of what's going on in somebody's mouth. And they had a weak hydrogel here, and they're characterizing it. So you see that the sample's coming down, goes through a compression step, and then it fills out the plate there. And then it may or may not rotate, depending on which test they did. And then afterwards, it pulls off again. And so you see quite a lot of information. This is with time, the normal force. As you squeeze down on it, it gives you a peak. So that's how stiff it is. And then when you pull the gap up, it gives you a minima. That's a negative fold. That's showing you how sticky that product was holding your tongue onto the palate. So we can see here there was a residual. So you squeeze down, there's a residual force. This is with some shearing. So you can see it dropped off there to 0 force, and then I open the plates up here and it pulls a negative force. There's another residual there. Squeeze down again. And so with repeated cycles of closing and opening, you can see how the material behaves as it would be in your mouth. So this would literally simulate chewing, or mastication as we call it. So you can see this product without saliva, the peak. So if you just take the peak, the amplitude here, this would be 0.25 or something like that on the first one. And you can see here that it's quite stiff, but with repeated cycles, it gets thinner and thinner and thinner. Now, if you add mucin, this is good for simulations of people with dysphagia and other things like that. Maybe they aren't producing the right saliva. You can have artificial salivas. And with mucin, you see it does actually work somewhat. It breaks the sample down with repeated cycles. Obviously, with saliva, it's the best. And it breaks right down in maybe 5 cycles. And then this is the stickiness and pull off. You can see that the thickest with dry, this is with mucin, and again, the least, it's with the saliva. So we can see the saliva causes the quickest decay and the extension of viscosity of the product. So we're doing a direct simulation of the mouthfeel of a product with a rheometer. Really, really useful. Now, another thing you might want to do is just look at tack. Let's say you want to adhere something with caramel, or make a cookie and see how well the cookie sides stick together to the pate in the middle of the cookie. You're going to do some squeeze and pull off testing. And so what we do here is we squeeze down on the sample and we wait a certain time, and then we pull up. And as you pull up, this is the part shown here, the gap opens up, right? So this is the gap in blue. It's the gap there in millimeters, and it's being pulled off. And this is the negative force. So that's how much it's adhering to the surface. And as the gap pulls up, you see the force become very negative. And that's the maximum tensile strength, if you like, of that food in the middle. And then you see it break away. Now, if this is a sharp detachment, let's say it just as adhesively fails, then you'll see a quick drop off here. Whereas if it cohesively fails, you'll see more of a U-shape curve in this pull away force. So you can see here the area under the curve that's automatically calculated with our sequence, and the peak pull away force, which would be your adhesion strength. And you can see how sticky material is. On the rheometer, very, very good software, and you can do amazingly good simulations. So somebody here created a loop, and they said set the gap down and then move the gap up, and it's just moving down a certain amount and moving up a certain amount. So you can see it's going from 5.2 to 4.7 millimeters, and it's just going to repeat that because they put a loop on it. And so you can see it goes down, up, down, up, down, up, down, up. And you can see here they're using blue tack or sticky tack. This is kind of a poster, a sticking tape, I think, but you can also do it with foods, obviously. And you can see here the results from repeated cycles. So sample A is a fairly soft tack, and actually you see it's got a peak force of 7 newtons and then down to about 5.3, and then it's dropping off quite quickly. Whereas tack, see it starts at about 40 newtons, sorry, force, and it's dropping off actually slightly quicker, but the forces are much higher than in this one. So you can see just from the amplitude of the force, this is a softer tack, this is a stiffer tack, but also from the pull-off, remember you can see this is cohesively failing, and this is adhesively failing, so it snaps away. So we can see the failure mode in this tack. So very, very useful test to quickly characterize the adhesive properties with repeated cycles and things like that. So there's so many uses of rheology in foods. Another one is tribology. Now, tribology isn't the bulk rheology properties like we normally use with cone and plates or parallel plates, cups and bobs. This is the surface rheology, basically the amount of friction that the sample is going to give. So if you imagine this is a lubricity measurement, how slippery is your food? Now, this has become quite relevant for food since people have been trying to remove the amount of fat in their food. And if you take all the fat out and the oil, then actually things become a little bit more stodgy in their consistency. They're not quite as smooth or slippery. So ice cream without any fat in it maybe doesn't have quite the same mouthfeel as a high fat ice cream. And so people try to characterize this using a tribology cell. Basically what you do is you smear the sample in the center here over the 3 plates, and then we will put this this ball on the top with a certain normal force. So you're pushing down on the bellows here with just a light force, and then you rotate it, and you see how easy it rotates. If it's very slippery, it will slip around easily, and if it takes more friction, then it's going to obviously show it's not very lubricating and it's not very smooth for mouthfeel. So here's our results. We've got a constant normal force of 1 Newton here, then red, and we're going at higher and higher shear rate, rotational speed here, and we're looking at the friction that's from the torque to rotate it. So in this sample initially, it's giving some friction. As you go faster and faster, it gets more and more lubricating. Maybe that's because the sample is getting in between the ball and the plate. On that previous measuring system, maybe it doesn't have the time to get out of the way, and it's causing more slip behavior. And then eventually you get this increase in viscosity. This is where it's really not quick enough to move, or maybe the material's lubrication it's just not low enough molecular weight, and it can't move around quickly enough, so it just doesn't slide easily above a certain speed. And so you can do this with any oil. You could do it with lubricants and things like that for industrial uses, but obviously the lower shear rates would be useful for simulating mouthfeel in your tongue and things like that. And so there's some non-food examples here. This is sapphire grease, and then Vaseline, and ophthalmine, that's an eye drop, and then there's U2400 oil. So I apologize, I don't have a lot of food examples here in this one, but you can see here that the Vaseline, so fairly low viscosity, this is fairly slippery, whereas the ophthalmine maybe didn't give such a good lubrication, and the grease was even thicker. So you get an idea. That's the tribology cell. Another thing you could do is 3-point bending and texture analysis. So we have a range of texture analysis tools for the Kinexus. This is the 3-point bending fixture. There's a narrow one, and then there's the 35-degree cone and the 70-degree cone, which can be used for penetration. So if you want to look at yogurts or cheeses or lard or other things like that to see how stiff they are, then you can do penetration on the instrument. So very, very versatile. You can do rotational and pull off and squeeze flow. And this is my colleague Shona is dunking cookies into her tea and then testing them, right? So quite a common thing to do. And what you don't want to do is dunk your cookie and then it actually falls in half and you have half of your cookie floating around in your tea. You just want it to be kind of nice and moist. And so we can see here, stale cookie gives you very high normal force. A fresh cookie's got a nice snap to it. And then the dunked cookie, obviously not too soft, it didn't fall apart, so that's good, but much softer and breaks at a lower strain. So we can see the effects of all kinds of things you might do to a product with regard to texture analysis. These are chocolate fingers, and Cadbury's chocolate fingers can either be just chocolate coated or there's white and dark chocolate coated. Obviously that would give you a higher breaking strength. Here you see it breaks at just over nearly 9 newtons, whereas the regular chocolate finger breaks at 4 newtons. So you could use this for cheese stiffness. You could use this for all kinds of other products. And I think that's one of the last examples here. I know we have microscope stuff coming up. This is dough baking. Now you can actually bake in the rheometer. So if you put some dough in between the plates and maybe you cover it up with a cover like this to stop the sample drying out particularly, because you don't want it to form a crust at the rim, right? You want it to really bake more uniformly. So this would just prevent drying. And if you set the normal force to 0, right, as you oscillate, you're measuring the modulus, and as you do a temperature ramp, you'll actually simulate the oven conditions. So the sample will actually bake in the rheometer, and as it starts to swell, if it's bread, for instance, you'll actually see a normal force on the plate. Or if you allowed the force to stay at 0, you'll actually see the gap change. And so this is a really good way of seeing how much your dough will rise. And you can see, therefore, the strength of the wheat gluten, whether it's a strong or weak wheat gluten or not. So all kinds of very interesting tests you can do with actual baking. Obviously, in these real hydrocolloid simulations, in these real tests, data gets a little noisy, right? Because you have things bursting and bubbles popping and things like that. And so we've got here a product which is elastic. We've got the elastic modulus in red. And as you heat it up, it's getting softer and then it starts to bake, right? So now it's rising and it's getting thicker and eventually it's fully baked. So you can see how stiff the bread is. And also, if you looked at normal force, you'd see how much it rose as well. So we can see the effect of changing the heating rates, obviously changing anything in the formulation. And the nice thing about this is you're actually getting quantitative results. You can really quantify what's going on with your mixture. You could also optimize the processability of that. You know, how long do I need to mix in the yeast to get it to rise properly, for instance, and things like that. So these processes are, you know, kneading and stretching and molding. You could also do these on a rheometer if you wanted to, by looking at the oscillation and the viscosity profiles just outside the linear viscoelastic region. And those are test methods called large amplitude oscillatory shear, LAOS, or within the linear region would be SAOS, or small amplitude oscillatory shear. Now, some people actually want to look at the product while it's being tested. And so you can do this with the Rheo microscopy cell. And so we actually use a quartz lower plate here. It's temperature controlled. And then we're going to put this microscope up underneath and we can actually view the sample. If you want to, you can attach it to a UV lamp. Instead, this is a UV lamp with a light probe. But if you take that out, you can put the microscope in there. And it fits in this bayonet holder. And so we can expose different diameters of the sample to UV if you want to, or we can just look at it in a microscope with different focal lengths. So this is the microscope with the LED lights around it. So this is very nice. You can change the radius that you're going to look at, and you can bring it up close. You can change the magnification on the microscope and the brightness of the lighting and things like that. And so we can actually look up from underneath. And I wanted to see how good this microscope was. So I put it on there, a reticle, which is a particle size reference slide, which they use in microscopy. And we can see here a line of 4 micron dots. That's actually pretty impressive. An 8 micron, 16, 32, and 64. So even 4 micron particles you can see under this microscope, just looking at it. This is the OptiTechscope, actually, which is available for the Connexus. But you could obviously supply any microscope you wanted. And the idea of this is that you can look at products before, during, and after shear. So for instance, if you have an emulsion, and an oil and water emulsion, you want to see how big the particle size is. Maybe you're going to look at the particle size initially, and maybe then you will shear it, and you will see obviously not much because it's blurry as it's spinning around very fast. And then afterwards you stop shearing it, and you can see if the particle size has broken down to very small particles if you shear it fast enough, or maybe it started to break down that emulsion. Maybe it's just now homogeneous or whatever. So you might invert the emulsion if it was of the wrong concentrations and things like that. So you can see stability. You could obviously do temperature ramps with this as well. This is a picture of mayonnaise, which I borrowed from Ian Hopkinson's website. And you can see here, it's very clear to see with the microscope, the oil and water droplets. Nice picture with that. And this is basically what we're doing. We're looking up from below the lower plate at the sample. And you can do that with an oscillation as well. And you can do it with a temperature ramp. So you could see as you reheat the sample, when is it ripening, or when is it going to coalesce, and things like that. So these are the key parts of the rheometer. We've been talking about the Connexus, and we have the geometry, the upper one, and the lower temperature controller. This is modular. You can just unscrew it, take it out. I'll pop out here the geometry easily by pushing up on the chuck, and then here's the motor, and this all plugs into a PC with one USB cable. And we can attach onto this instrument lots of different fixtures. So for very low viscosity liquids, maybe you use cup and bobs, double gap cell and things like that. And as you get to thicker, maybe you go with a Conan plate or a parallel plate. If you've got a very stiff gum or something, you might want to use a small parallel plate to test it. Or if you really have a stiff stick of sample, we could do torsional measurements. There's a torsional fixture for this too. And you can measure wet versus dry testing. So all kinds of different accessories, and you really can test almost anything from as hard as a composite down to low viscosity liquids, all on the same instrument. So the Rheology logo we've got here is Connexus, and we've given it the tagline, more Rheology, less effort, because it comes with software which has got all these pre-written sequences in it to make this more of a turnkey system. You can use it without really having to reinvent the wheel and do everything from the ground up. So there's over 100 pre-written test sequences in the software with common problem-solving things. So that's a quick overview of the rheology of foods. And I'm sure I haven't answered half of your questions, but now we have a chance to do that. So if you have a question, please type it in, and we'll go through them.
Yeah.
Thank you so much.
Thank you, Phil. Thank you, Phil, for your nice presentation and the overview. And we already have a lot of questions here.
Okay.
So, but
yep.
Please keep them coming. I will just now start with the first question, which has always also something to do with the software. And the question is, for the screw bob to help resuspension, how is the shear surface corrected? And is this already done in the software?
Yes, so we calculate the surface. I mean, the shear rate obviously would be slightly less precise than a single shear surface. But so it was done with a least squares fit model. It was actually published as a method that John Duffy and Samuel Amin published on this in one of the rheological magazines. So we can calculate the shear stress and shear rate constants for any geometry. Obviously, as they get out more variable, like the paddle, you know, things like that, then the shear rates vary widely across the surface, and the results become a little bit more relative rather than absolute. But for average viscosity, we can calculate the average shear rate and the average shear stress, and that would correlate directly with the C25 in that case.
Perfect. So the next question is about recovery tests. And are they always run with dynamic oscillation, or are there situations where static shear would be applied?
Yeah, so there's two ways of doing this test. You can either do shear oscillation, shear oscillation. So you oscillate at the beginning to see the initial modulus, and then shear it a little bit, and then you oscillate at the end. Now that would simulate stop, go, stop, right? That would basically not move and then flowing and then not moving. So if you want to simulate stop, go, stop, then it would be oscillation, shear, oscillation. But if you wanted to do low shear, high shear, low shear, you could also do that. So that would be a 3-step viscometry test. And that's actually also another option in the software. So there's a 3-step viscometry test in the software if you wanted to do that too.
Great. I have a question about the Rheo microscope. What temperature does it have generally?
Yeah, the temperature range of the Peltier cylinder is what controls that. So it goes from -10. I think if you put a chiller bath on, you might get colder, maybe -20. But it goes from about -10 up to about 200 degrees C. But I would say because of the quartz not conducting quite so well to the center, you probably get to about 150 degrees C. The microscope electronics should be fine because it's not actually in contact with that heated surface at all. So I think that should be fine. From -10 to maybe -5 to 150 degrees C.
Okay, great. Regarding mastication, did I pronounce that correctly? Sorry if I didn't. Can you measure extensional viscosity with a common rheometer?
Yes, so extensional viscosity is quite difficult to measure, but you can measure it with multiple ways. You can measure it in shear with a measurement of N1, the first normal stress difference. You can measure it with a capillary rheometer by, what's it called? There's a method you can do with 2 barrels, you know, a long and short die, Cogswell's model. But in this case, we would be doing a direct pull-off, which actually is the most direct way of measuring extensional properties of something. You can also do lubricated shear. So you squeeze 2 plates together, and you can see the extensional properties from the normal force in that. So there's multiple ways of looking extensional. And if you want to know more about that or discuss it, we can just talk about that later if you like, email me.
Yeah. Great. One more, and I think then we will close down this webinar. How would you account for the reproducibility of rheological tests? Would you run in triplicate and show all the data, or would you average each point? Or would you simply choose to present one set?
Well, that's a good question. So I guess it really depends on your scientific background and what the purpose of the study is, right? If you want to, if you're doing a medical trial or something, then you'd want to give very comprehensive data with lots of repeats. But if you're just looking for a trend in a mixing process or different additives added to a food component, then it's probably good to firstly establish how reproducible a method is. And you do that by running the one sample 2 or 3 times, maybe 4, 5, 10 times, And once you've established how reproducible it is, like I'm getting my results are X plus or minus Y, then you could just run the samples 1 or 2 times each. I often establish reproducibility with one sample and then run everything else once, because the samples are so different between each other that the reproducibility of the test method isn't usually an issue once you've resolved that. So things that like reproducibility of loading will cause an issue, or sampling and things like that. But once you've worked out how best to load a sample and take a representative sample, you can get pretty reproducible results. You look at things like thixotropy and that, and do a pre-shear, rebuild time. And with those preliminaries, you can usually make your test fairly reproducible, and then you don't have to run every sample 10 times. You just do it in a reproducible way because you've got the method sorted.
Great. Thank you, Phil. Just a few remarks, because some asked if the recording will be sent out. Yes, you will receive an email tomorrow, probably, with the recording of this webinar. And you can also have the slides. Just drop us an email at webinar_ngb@netsch.com. And if you want to contact Phil directly, you can either go to his LinkedIn account, I guess, contact him via LinkedIn, or use his email address, which is philip.rolf@netsch.com. Is that correct, Phil?
It's absolutely, yes. philip.rolfe@netsch.com. Yep. Well, if you actually email the help desk, I'll get it eventually. Yep.
Yeah, we will find a way to get the questions to you. You can also use any email address you find on general contact address you find on our Netsch website. So Phil, thank you very much for your presentation and for answering the questions. To everyone, thank you very much for joining us today. Check out our upcoming webinars on the website, and hope to see you soon.
Thank you so much. Thank you, Milena. Thank you, everybody, for coming. I hope you have a great rest of your day. Thank you. Bye-bye.
Bye-bye.